Okay, so we were looking last time about the cascode part, and one of the things which I said last time about cascode amplifiers has the advantage. I am just recapitulating what we did last time, and we said you can increase the gain without loss of gain bandwidth product points, and that is the strength of cascode over cascaded system. And essentially this is what makes cascode very interesting. However, you may find in many applications cascodes are not used in fact. Okay. I am not saying it will never be used. There are different variety of cascodes op amps are available, telescopic or folded or otherwise. Each has some value, but they are not the ones which are commonly used, okay, for every purpose. Specific purpose, yes, cascode is the best amplifier. In most cases the amplifier which I will use is we shall see later, simple one stage, two stage amplifier, which is good enough for many applications. But in the integrated circuit you will be suddenly actually told to match with something else in a digital domain, or its inputs is very different, and then you need specific amplifiers to drive that. So why we are teaching this? Because these are the real life systems in which any odd applications may require any odd kinds of amplifiers. Okay. However, we will first learn basics, and when the application comes, okay, now we know this you want, so this is better for you. Okay, that is what the designer should know. If this is an application, this is the input it has to, then what amplification I should have so that it can drive better. So this fact last time I said that cascode amplifiers are superior to cascades, because in cascade the gain bandwidth of a single stage remains constant for any cascading stage, and therefore as you increase the gain by cascading, the bandwidth keeps going down. If you have 3 stages, the bandwidth will further go down. Whereas in cascode the gain bandwidth product does not change even if you boost the gain, and that is something fantastic about cascodes. Penalty, we shall see soon what is the big penalty we pay, at least in integrated circuit that is a big penalty we are paying for all of it. Okay, so this is what last time I was talking. So I will start again. Basically I start now my amplifier. A typical cascode amplifier shown here is driven by biasing current of IDS, fixed current source as such you can say, and we want to find the gain of this amplifier, and we also want to find its gain bandwidth product. Okay. Now the way I write that we have been already designing amplifiers. What is a typical amplifier? Last time I showed very simple amplifier, just few seconds. A simple amplifier we have discussed already, can have a current source, load or whatever biasing you wish, and this is your V in, this is your V out, okay, and we are interested in this amplifier is V0 by V in, and we know typically this will come minus GM times R0. We have derived this earlier, so we just know this. So what now I am going to do is, I have a cascode which has more than one transistor sitting there in series there, and therefore I will say can I get GM effective and RO effective so that the gain remains GM RO. Okay. So instead of just GM, for the cascode I am saying GM effective into RO effective, and if I derive these two values for this cascode case, I still have the gain which is minus GM effective into RO effective. Now this is what follows, and therefore I thought before I start you should know that I am basically trying to replicate what I already know and convert that into my earlier knowledge. Is that okay, all of you? So of course after all this, when I will show you the actual solving circuits is the best way of doing things using Kirchhoff law. So some other amplifier I show, okay, you do not know anything, fair enough, you can always put equivalent circuits. Okay. So I will show you some examples of solving with any kind of 3 3 series, 4 series or n series or n parallel, anything can be connected, and then we can have equivalent circuit which may become quite complicated sometimes, but can always be solved using Kirchhoff laws. So it is not necessary that this technique which I show you is the ultimate or something, but this why we chose this kind of this is actually trying to compare with the earlier amplifier. So if I do you equivalently that, then you say okay, in comparison what is going on. Okay, so is that clear? As I say, I am this method which I am showing you is only to show you comparisons. This need not be always used by anyone, but can also be used if you feel so, okay, nothing very great about. So okay, then we say if it is equivalent transistor situation is I is equal to GM effective times Vn plus GO effective times V0. As we did for normal amplifier, instead of GM and GO, I will now say, maybe if you, I should do something like this. So we can write that AC current through the for this equivalent amplifier stage will be I is equal to I is the current through the amplifier. So GM effective times Vn plus GO effective times V0. We are already done for common source normal, so this is the extension of that. So what is the game I am trying to say? I will figure it out what is GM effective for the cascode and what is RO effective or GO effective for the cascode, and continue to use this same method of solving further. Is that clear? What is the method I am suggesting? I am only trying to, why I repeat, I want to see how much that GM effective is different from single stage amplifier GM and how much RO effective is different from RO of the single stage amplifier. Does that change? Because you said gain is boosting, okay. So that means that GM RO product must be increasing. So it is possible that GM effective may be higher and also RO effective may be higher, or one of them may be higher, other may not change, or vice, whatever it is. There are possibilities. We like to see which one is really pushing the gain, okay, and why then in spite of increasing gain the GBW or gain bandwidth point does not move, okay. So that is this. So okay, to say it, let me put it, this is a capacitance C which is load capacitance. This amplifier is driving a load capacitance. This load capacitance is such that all other capacitance can be neglected except the output capacitance, which takes as a net load capacitance. Is that clear? Remember, bandwidth can be a function of input capacitances, series capacitances and output capacitance. I say this is giving you what we call dominant pole as of for the case of solving. So we start with the case 1. I say if V0 is 0, in this expression I is equal to GM effective Vn, then GM effective is I by Vn when V0 is 0. Just substitute 0, so GM effective is I by Vn, okay, when V0 is 0. Look at this expression, put V0 0, so I by Vn is essentially GM effective when V0 is 0. Now similarly one can say if Vn is 0 and then we figure out I by V0 is nothing but GO effective. Is that okay? Just either this 0 or this 0. So I want to solve these two cases when VO is 0 and Vn is 0, and this equivalently then I get GO effective is I by V0 and GM effective is I by Vn. So now I want to find I and Vn ratio or I and V out ratio for the two conditions which I have written here. Is that okay? As simple as that, nothing great. To make V0 0, I say it is a fixed V, so no change, so V0 is 0 there. Let us say I flows through this, both transistors should have, okay, please remember for an AC circuit any DC point is at 0. So V reference, which is a VDC for this, is essentially grounded for the AC purposes. So for this, if I say this point is 0 and then I solve I by V in ratio for this circuit, then I will GM effective. If I say V in is 0 and I measure I by VO2 here, then I will say I will get GO effective. So this technique is simple, and this is only, as I say, keep trying to equal the GM and RO values of earlier this, so that I see comparisons. Is that okay? So the method is trivial to some extent, but it does give you some physics behind what is going to happen. Okay, is that okay, everyone? Okay. To start with, of course in reality this may not be necessary, but in most integrated circuits, unless specified otherwise, transistors are always made equals. Okay, for a variety of reasons we shall come to see. Actually if they are not identical, it creates hell of an issue. Okay, so we will try to make transistors identical in many cases, but if needed we can modify. What that change will be, normally thresholds are rarely changed, only it is the W by L ratio which may be different for two cases. Okay, so now right now for the simplicity I assume M1 M2 are identical, that is the thresholds are same, the W by Ls are same, and everything else is also mu is same, C ops is same, everything same. Okay, for the transistor M1, this is the lower one, the current flowing in this transistor VGS is nothing but V in, VGS for this M1 is V in. So beta V in minus Vt square into 1 plus lambda VO1 is the current flowing in M1. Is it clear to you? Beta times VGS minus Vt square into 1 plus lambda VDS. So I just substitute. I am not actually using, I am just trying to show you what current is flowing there. However, if I only look this transistor from the small signal point of view, then I say here I is equal to GM1 times V in, GM1 times V in is the current source going out, current going in the output, plus GO1 of this into VO1. Okay. Now for this transistor M2, slightly the current is similarly now I is equal to beta 0 minus VO1 minus Vt square into 1 plus lambda minus VDS is 0 minus VO1, 0 minus VO1, so it is substitute. This can be a current in M2. Please remember these two currents should be identical, because in a circuit only one current can flow, one circuit point. However, I write similar expression for I in for M2, so I is equal to GM2, and what is VGS for this transistor? 0 minus VO1, is that correct? What is the VGS for M2? 0 minus VO1, so it is minus VO1. I repeat, what is VGS for this M2? Gate voltage is 0, source voltage is VO1, so 0 minus VO1, so GM2 is into minus VO1 plus GO2. Now how much is VDS? 0 minus VO1, 0 minus VO1, so 0 minus VO1, which can be written as minus GM2 GO2 into VO1. Is that correct? Is that okay? So I have an equation which gives me relationship between for M2 and M1, and what is the ultimate aim I am looking for? What is first I am trying to derive what? GM effective. So what value I am really looking for? I by V in. Okay. So this equation is what is important for me. Okay. So I want to find GM effective, so I want to find I by V in, all small signal, all small signal is always valid. It is, we had just told you other day, V small. Okay, I think you should now go back and do some little more calculations yourself. The way small signal analysis is done in any IV characteristics, let us say this is the characteristics, any idea. What we fixed is this DC point, is that clear? And superimpose on this some signal, assuming that the slope here does not change. So small signal analysis currents are similar, except that the DC value has been taken out of it, essentially saying I total is IAC plus IDC, V total is VAC plus VDC. So any time we substitute the DC value together and subtract, so the difference is only AC. You subtract total minus this, so you will get the AC value. So the expressions are valid. The current I is so adjusted that both M1 and M2 are in saturation. Is that clear? So I has that is what I say, bias point is fixed by IDC, this value. So if I fix that value, I am making device saturated. If it does not occur, yes, I will have a problem because there is no gain, then possibly I may not get enough gain or zero gain sometimes. But I assure you, as of to solve this problem, that I is so adjusted that the device, both devices can enter into saturation. Is that clear? The only word which I have not stated, which I soon I will say, there is another word which I will going to use, is called headroom. Okay. What is that word, headroom? That how much maximum I can shift, that device still remains in saturation or go below till remains in saturation, is called headroom. I have that play available. Okay. So I assume that my device has sufficient headrooms, so that device remains in saturation. This is assumption which can be proved otherwise. It is something saying that first you assume and then prove, that is all mathematicians do, so why not we do it. Okay. Small AC signals. As I say, you add total VDC plus VO everywhere DC and subtract DC value out of it, you will get similar equations. Is that clear to you? Very small. As long as you are in a small signal, this is all small signal circuits we are solving. As long as you keep doing this, it is fair enough, though no matter, either you may say, if the slope slightly goes away, your headroom is so small, then you actually will never remain in saturation. So where do you bias is a very crucial point for us. Okay. Okay, right now we will come back to this issue in case it is needed, but let us move quickly. So from that first second equation which I just derived, VO1 can be derived as minus I divided by GM2 plus GO. Just now I wrote an expression, I now want to find VO1 and substitute this VO1 in that equation for M1. Is that correct? What did I do? Evaluate VO1 from M2 and substitute in value for M1. Okay. So if I do this, I get I is equal to GM1 V in, which was the term anyway there, and I have GO1, VO1 was the product there, so it is VO1 is now replaced by this minus I GM2 by GO2. Then I collect I terms, so I is equal to 1 plus GO1 upon GO2 plus GM2 is equal to GM1 into V in, and then I evaluate GM effective. As I say, better method survey is what? Put a equivalent circuit and solve, nothing better than that. But why I keep saying you why I am using this technique, just to show you how much difference we will do if I go from single stage to cascode, because that gives you some numbers immediately to see. This may not be the method you should use for real circuit solvers, okay. Even SPICE does not use this. But why I chose this is not even given in many books, because people do not believe that this is way but I want to explain you how much cascode is really affecting you, okay, and this is the way of explaining that. Okay. So I is into 1 plus GO1, just collect this term on the other side, and I is equal to 1 plus GO1 by GO2 GM2 is equal to GM1 V in, and therefore GM effective is I by V in, that is what you said. For this condition we already said VO2 is 0, we have already assumed, and for that we have solved. So GM effective is GM1 upon 1 plus GO1 plus GO2 GM2. If I connect the term properly, I will get GM effective is GM1 times GM2 plus GO2 upon GO1 plus GO2 plus GM2. Is that okay? Now GM typically is transconductance of an amplifier, should be higher or lower for a good amplifier gains? Higher. So typical, and G0 which is 1 upon R0, that means G0 should be very small if you want larger gains. So in general, since the output resistance of a transistor is the order of mega ohms, typically GMs is the order of millimoles or millisiemens. Okay. Since this is milli and that is mega or 1 upon micro you can say, so GMs are always much higher than GOs. Of course, given a value please check it, device is still saturation and this is valid, if not use the full expression, I am not saying. But let us say GMs are much higher than GOs, which normally will be in 2 to 3 orders, then you can leave GOs and figure it out. This term if I leave GO2, so GM2 plus this compared to GM2 plus GO2 I leave GO1, this by this is 1. So effective GM is nothing but equal to GM1. So after even cascoding I have not really modified my GM term. It is modified, I am not saying it is not. If you substitute this value it will be slightly different from the just GM1 because this term is slightly larger than this. GO is smaller, but let us say it is 10, this is 10 over minus 3 minus 6 minus 6. So even if there is a slightly more value in the denominator, but ratio wise it is extremely small, 0.99999 something kind of thing. So we say practically GM is effective is GM1. So one of the feature of a cascode was that it did not change GM. Then if gain has to boost, we already said what is GM, gain is GM effective times RO effective. So obviously if your GM is not changing, the other term must be getting boosted, otherwise there is no way I can boost the gain. Okay. So then we must now evaluate RO effective and figure it out how much it is more than the normal RO I have. Okay. And if it is much higher, that means my gains will be proportionately higher, is that correct? The ratio of RO effective to RO is essentially times that much times the normal gain will be boosted, okay, without losing GM value, is that correct? Now we will see why we are interested so strongly talking over GM. So is that in cascode we have not gone out of our everything done, okay, we just say GM effective is same as GM, is that okay? Everyone has written? Okay. Case 2, I want to find RO effective. So what is the technique we said? Put V in equal to 0, is that okay, for AC everywhere, this is anyway grounded, and put a output voltage V0 which enters a current I. This is a standard method of finding output resistance. Short all independent voltage current, open the current sources and short all voltage sources, independent ones, is that clear to you? And then apply a voltage at the output and measure the current there for the circuit V by I, there is the output resistance. So same technique has been employed by us, is that okay? So okay, for M1 transistor Vn is 0, so Gm1 into 0 plus Go1 into Vo1, or to say Vo1 is I by Go1, is that okay? For the transistor M1 Vn is 0, so Vn is 0, so Vo1 is I by Go1. Okay. For the M2 transistor, the upper one, maybe I should write, I think you already have that, but for the M2 transistor the current is Gm2 times Vgs. How much is Vgs? 0 minus Vo1, so minus Vo1, and how much is Vds for this Go times Vds, or this minus this, so V0 minus Vo1, is that okay? I collect the terms again, minus Gm2 plus Go2 into Vo1 plus Go2 V0, just collect Vo1 terms, okay, and then substitute Vo1 from this into the second one. Last time what did I substitute? I picked up from M2 and substituted in M1, now I picked up from M1 and substituted in M2, then I get I is equal to minus Gm2 Go2 by Go1 into I plus Go2 V0. Just substitute Vo1 from here and you get these expressions. What do I then collect? Collect I terms and then Vo by I is Ro effective. I collect I terms and then Vo by I is the output resistance as seen from the output terminal, okay, net. So okay, so I collect the terms of I and then figure out I by V0 is Go effective, substitute everything and I get Go effective is Go1 into Go2 upon Go1 in plus Go2 plus Gm2 and I invert it to make it Ro effective. So Ro effective is Go1 plus Go2 plus Gm2 upon Go1 Go2, divide this each term 1 upon Go2 plus 1 upon Gm2 Go1 plus Gm2 by Go1 into Ro2. Okay. Still do some collection of terms and you get Ro1 plus Ro2 plus Gm2 Ro2 Ro1. What is the Ro effective? Ro1 plus Ro2 plus Gm2 Ro2 Ro1. That is something fantastic is happening. Okay. But what is Gm2 Ro2? The gain of second stage amplifier individually, is that correct? So AV2 we can say. If you are noted down, I will just write down the expression. Okay, so if I collect all this term and write Gm2 Ro2 as AVO2, then I get Ro effective is precisely, if you seek it, I think there is some mischief here, this will come Ro1 into Ro plus that Ro2 term should not AVO2 into Ro1. ये सब तो ठीक है. So Ro2 plus AVO2 Ro2, Ro1 and Ro2 are equal. Why are they equal? We said transistors are equal, currents are equal, 1 upon lambda ID is constant, so Ros are equal. So essentially what is it trying to tell, and gains are typically of the what order? 100 to 1000 to 10,000, maybe 10 million. Gains of amplifiers can be as high as 1000, 10,000, a million as well. Okay, 10 to the power 6 gains are possible. Not that every time we will use them, but possible. Op amps have 10 to the power 6 are anyway available, is that correct? Gains are available. So normally AVO2 will be very high compared to any other term there, okay, and neglect all Ros, but AV into Ro will be heavily increasing the Ro value, okay. AV is 1000 and Ro is mega ohm. So from mega ohm it has gone to giga ohms, okay. So now the output resistance of a cascode amplifier can be boosted by this AVO2 term, okay, and if Ro effective is so high, AV0, which is nothing but Gm effective into Ro effective, is as much high, though Gm effective is same as Gm1, is that correct? Gm effective is same as Gm1, but Ro effective is gain times the Ro is now pushed there. One of the stage gain AV2 into Ro is boosting the gain Ro, and therefore the gain equally get. Now we were making a statement, okay, that if I would have done a cascade, what would have been the gain? Instead of putting cascode, let us say AV1 is the gain of first stage, AV2 is the gain second stage, and they are equal, then it will be AV square, is that correct? So here also if you see, if you just look at this expression AV0, it can also be expressed in, do not write all of it, just write this function, AV0 is AVVO1 plus AVO2 plus additional this. Since AVs are much larger, square terms are larger than single terms, so typically gain is gain square same as what cascade could have got it, is that clear? Cascade could have got how much gain? Square of two of them. Here also I am getting same gain, little more but almost same order of gain. Then what did I achieve? I have, you said gain is boost, no, gain product it seems to be similar for the case of cascade as well as cascode. But what is changing or not changing is the gain bandwidth product, is that point clear? The effective gain probably in a two stage cascade is same as one single cascode. It has not, of course additional term is there, so you may say yeah it is still boosting, but in 10 to power 6 plus 10 to power 3 it is still 10 to power 6. So it is a gain is only AV square, it is not really boosted as one thought. But then what is that I keep saying boosted? From the single stage I have only used one single stage there, okay, and I have boosted the gain from 1000 to 10 power 6, okay, which is what I did for the cascode, because RO effective I could boost 1000 times, okay. Now the term which is most important for us, as I say you write down this expression, they are simply derivable and there is nothing great about. The point I was trying to make is essentially cascode single stage is not very great compared to two stage cascade, because we are comparing all the time with that why not connect two amplifiers in series, which is always done many places. So what is this cascode is actually doing, okay. So we say okay, there what was the problem I said, if I make AV1 and AV2 there or AV square, the gain bandwidth will have new gain, but the bandwidth will go down because GBW is constant, okay. So as I keep putting cascade stage, my bandwidth will keep on going reducing by that number, but that is does cascode does the same, then why do it cascode? If it does not, then we say I have beaten up. Please remember GBW to some extent is called figure of merit or technology constraint, okay. We always say GBW is constant, kuch nahi kar sakte. Now with cascode can we beat this so called technology constraint, and here is that expression. Everyone written down this? This is what it is saying, gain bandwidth product of a cascode is GM effective by CL, but what is GM effective? GM1 by C effective, is that correct? C effective means CL plus any other capacitance you put there is fair enough. The gain of a cascode is AV square, the bandwidth is GM effective by CL, GM effective is how much? GM1. For a single stage the gain bandwidth product is GM by C, because GM1 is this, which is same as the earlier one. So what is it trying to say? Gain bandwidth product of a cascode is same as single stage amplifier, but from the single stage amplifier what has it changed? Gain how many times? 1000 times or whatever the gain of that amplifier initial this, that many times I have boosted the gain, but my gain bandwidth product has not changed, is that correct? So that is something I achieved, that I have not missed the point of GBW, but I still boosted. Please, I last time showed you some figure, maybe I will repeat for you. You just write down this. In the case of cascade, what would have I lost in case I boosted the gain? By that much amount I would have lost the bandwidth, is that correct? Now I say no, gain bandwidth is not changing even with the cascode stage, but gain has been independently as if boosted by me, is that clear? By increasing the this, because GM by CL is no different from GM by CL for the two cases, so the GBW point did not move, okay. That help that GM effective is GM1 has helped me now to fix that point independent of which amplifier I use that. So here is the figure, we will come back to it, okay. Maybe I should draw better figure, just a minute, I will come back to this expression once again in case you have not written. Let us say I have an amplifier which is gain in dBs versus frequency. So this is my gain, and let us say it has a single pole as I had taken the case. This is my GBW, this is my AO1 or something. If I would have boosted the gain, okay, so what, and this is my bandwidth. If I have boosted the gain for by cascading, let us say I go here, okay, then this bandwidth point would have itself, sorry. So what is the change would have occurred? BW original and BW new. So I would have lost the bandwidth. I increase further, I would do this, again this, further bandwidth will go down. Now if I do the same thing for Cascode, what I am doing is the following: A versus omega. This is my normal single stage amplifier, okay. Now I am boosting the gain, okay, I am going from here to here, okay. I may still lose some bandwidth, I am not trying to say, because that ratio is not exactly 1, so some part I may, but the slope is such that it still meets the same point. So what has changed? Of course it should have been slightly this side, okay. So bandwidth reduction is still there, it is not that it is not there, but it is, the way figure is not very good, it is very close to the original bandwidth. But what has shifted? The gain. I have boosted the gain to keep the same slope. Now my bandwidth slightly is going down, but marginally going down, and I say as if I am not even worried about that small change. So I say okay, I am retaining bandwidth what I had, but I have boosted the gain. Is that correct? That is the strength of Cascode. Okay, we will solve an example, give you the result. Okay. I agree, but it is not related only to that, that is what I say, because this geo effective has many terms, so is GM effective. So overall, since you have to meet GBW, if you extrapolate it for higher gains, essentially what I am saying, you keep extrapolating that value, then you will find gain has been boosted, but bandwidth is not reduced in the same ratio. Is that clear? That is exactly the strength of Cascode. Now catchword in this all game was, which is why I said you all the figures and everything, was this, which you should realize what I did actually. I just fooled myself, okay, and I said okay, this last line you can read down, that is most important. The gain bandwidth of Cascode is same as gain bandwidth of a single stage amplifier. However, AV0 is AV square. Clearly the technology constraint is now new is under root gain Cascode into the old GBW is now constant. Is that correct? Because the new gain square हो गया ना भी वो, Cascode में gain square आया, single stage में gain ही था, तो equivalently it is gain under root gains this of Cascode multiplied by old GBW is the new constant which you have got it. This is called the new parameter figure of merit for a amplifier. Normally this would have been your figure of merit, I have now crossed that limit, okay. That is exactly what I was trying to achieve. Think of it, how did I solve? So gain square into bandwidth is now constant, not gain bandwidth. That is something is great we have achieved out of this. Is that clear to you? Because further increase will shift now you, I mean it is not that infinitum it can go, okay. Is that clear to you? So it is no, bandwidth is reducing, it is not that, but it is gain square time bandwidth is constant, not gain into bandwidth. Now all this game which I did not show you or did not say specifically, if you see your Cascode amplifier, once again very seriously, I am just trying to fool myself. I kept on telling this is a single stage Cascode, okay. Yeah, it is called single stage Cascode, but in reality it is also cascading two things. You have one amplifier which is common source, okay. Output of a common source which is VO1 is fed to this amplifier which is common gate, okay. So I am actually cascading two amplifiers even now, only thing is instead of two common source amplifiers, the second stage now is common gate, and the advantage of when I now show you common gate, this will be very obvious. Like in the case of common base amplifiers, the current gain is unity, same is in this case. The common gate amplifiers do not give you any current, because source current, drain current same, so it is almost unity current gains. But what is the advantage? It allows you to shift the, let us say what is the first stage is doing, Raj, you look at it, M1 is a common source amplifier. So what does common source amplifiers characteristics? Converts voltage into current. Common gate amplifier improves the output impedance, just now you have said, so what, and still available, gives the same current. So what has improved? The current source equivalent, voltage dependent current source has become far superior compared to single stage. Is that clear? So I have not really achieved fantastic or something I was trying to boost every time, but the idea was to show I have improved the current source from a normal stage amplifier, which has now higher output resistance, which is a good current source. How higher output resistance means good current source. All that I have done is by this technique is to improve good current source, which a normal VC normal voltage to current converters have. Relatively RO is not very bad even there, 10 to the power 6 or kind, but this has actually how much I want for a good current source? Infinite. So by boosting this, I am trying to get better current source out of the amplifier. Is that equivalently? So actually all statement घुमा फिरा के ये है कि बात कोई बड़ी नहीं थी. The funda point is that if I connect the two, which way can get me what really I am looking for. So analog design का ये issue है. 3 amplifiers we will discuss quickly from the Radhavi's book, common source, common gate, source followers, and we will see which ones have what property and when connected what it will do for you. Is that correct? So as a designer, I will do analysis, because at the end I have to know values, so I will have to do analysis, substitute the values, but I like to know a priori that which ones I should use for purpose spec of I am looking for, and this is what I am trying to hint every now and then, that this course is not just solving a problem, but just to tell you that by doing this I can achieve something which a priori I was not aware. I could solve a cascode, I will show you RO increase, but why I did all this? Because I figured out this actually can do this job. So if tomorrow there is some biomedical instrumentation requirement comes, you want a constant current to be driven, because the time taken for charging the input capacitor there has to be constant, ECG monitor. At that time you may require a cascode amplifier, because you need a constant current source as good as possible, other it has a time constant, it will not switch quickly. Okay. This is an issue which in real life applications one can see which ones to use. So as a designer I will not be told कि इसको analyze करके दिखाओ, but for doing analysis I will figure it out, what is that characteristics I get out of it, which when needed I can then apply. So the difference is that clear. Analysis is always required to prove a point, but you must remember the point is more important than the analysis. Okay. At the end we are doing all this to show, okay, if this need appears I will pick up this. Okay. Design. Now what people designers are expert about, as I keep saying, they are very good in copying, all of you are, but maybe all of us also. So they try to use someone else's result, but many a times the kind of value, some spec is not same between the two, and that may actually kill you the other way, because that is what the analysis really, if you do twinkle on this, this may also go, like GM effective here remain GM, you do something else, may that also changes, then the whole purpose would have actually lost to you. Is that clear? So in future the difference between analog circuit course and analog design course is only this, that we still solve the same circuits which we have done n times, but we now learn from them what is the advantage of using this. So these issues you should keep in mind all the time, because these are the only things which are required for a good designers. Okay. Given an application, decide, oh this spec, so can I do this plus this plus this, so that must strike you, and there is no solution for each case available in the market. Is that correct? So each application will require different thinking and therefore different design, and therefore people say it is slightly difficult because आपको दिमाग भी लगाना ही पड़ रहा है. Okay, ऐसे डिजिटल वालों के सामने ऐसा नहीं बोलना चाहिए, but to some extent yes. Sorry. हाँ. It's always gain bandwidth product. GM by C is a gain bandwidth product. I'll solve this right now. Take from me. I have not solved frequency response so far, so I have not come to it. I'll prove it what you are asking. It is always gain bandwidth product and not bandwidth. For a cascade yes, but cascade, that's what I proved you, that the GMC does not change but gain still boosted. Correct. Gain increased, which is in cascade did not happen, because any single stage I follow another stage, the gain, if gain increase, bandwidth automatically goes down. GBW may still remain, your point is, but the bandwidth reduction is too strong if I keep increasing the gain stages. 1000 times करोगे तो 1000 टाइम bandwidth नीचे चला जाएगा. Cascode does that, since it actually allows you slope to be modified compared to cascade, I am able to reduce bandwidth. I am still reducing bandwidth, but marginal compared to the cascade stage. We will solve a problem, plot a Bode's plot and show you where they match. Okay. Okay. Now before we go this cascade stage, okay, sorry, I am very sorry. Is this? Sorry. Just note down, I will come back to solve the values of this and then I will show you. All that I am trying to say, I have changed the constraint now. Okay, using cascade I have changed the constraint, because gain square ये आता है ना, ये gain square है ना, तो under root किया तो gain into gain bandwidth is gain square bandwidth. Gain cascade is AV square, under root of that is AV. So gain into gain bandwidth is gain square into bandwidth is now constant. Okay. This is the new constraint. Is that okay? Cascade is not a single stage amplifier, that is what I have proved just now. This is only true for cascade stages. This has been derived for cascade. Otherwise gain bandwidth is a constant single stage, we have done, put second stage, gain increases, bandwidth goes down, nothing you can do on that. That is sacrosanct. एक दोगे तो दूसरा हम ले लेंगे. No. It under root of that, that is the what I am saying, it will actually reduce by under root of that. I will give a value, I will actually plot the real values for that, then you will see actually slope changing is how much. Okay. Okay, I will check it, but this is correct. Okay. Okay. Someone says, is this gain increase is enough? Can I do something more than that? Yeah, I think Cascode people came out with another circuit. They say here is another Cascode amplifier which is gain boosted Cascode amplifier. Now already you have boosted the gain. Now I have an amplifier which further boosts the gain. What it should not change, again being Cascode stage, the GM should not change, but what should, therefore it increases RO effective. So you want even better current source now, yeah, another case in which I can have gain boosted Cascode amplifier. Okay, the method here is simple. In the first Cascode case, you just first draw the circuit and then expression. You start looking at my first and then you write. I have a same as M1, M2, here I actually put a ground there. The gate of 2 was referenced to a DC value or grounded for AC. Instead I have an amplifier sitting there which is receiving an input VO1 and transferring minus A times VO1 to the gate of M2. Is that clear, Raj? All that I did, that I have boosted, earlier it was 0 minus VO1, now A VO1 minus VO1. Okay, so it is slightly A plus 1 times VO1 is what now I am giving to the gate of M2. This is called boosted gains. or boosted ROs. Okay. Same way I can repeat the same expression for M1 and M2, okay, and figure out by same logic. Instead of VDS, what should I use for the first one? VDS, same as VO1, no change. For this the VGS is how much now? Minus VO1 minus AGB times VO1, is that okay? How much is this VGS? This minus this, what is output of first amplifier here at the gate? A. So A minus A times VO1 or AGB I call gain boost. So AGB times VO1 minus VO1, that is AGB plus 1 times VO1 is the VGS. Substitute there. This term does not change. Why it does not change? Because that this remains same, there is nothing change at the VDS. Is that okay? Only VGS has changed for M2, VDS has not changed for M2. So I am only changing the please, this voltage is the gate voltage which is minus A VO1, is that correct? This is still VO1. So VGS is minus A VO1 minus VO1, so minus A plus 1 VO1. If I substitute this, I get GM effective, long enough expression I derived, and if I say RO1 by RO2 is close to same, so these are ones, these are larger, these terms are larger, this can be neglected if everything cancels. So GM effective is still the GM1. So however, if I look at GO effective now for the same expression, instead of 0 minus VO1 where you are using, it should use 1 plus AG times VO1 terms. So now you are going to get GO effective is RO1 plus RO2 AV2 into 1 plus AGB times RO1. पहले ये AGB नहीं था, isn't it? So it was AV2 times RO1. So gain was resistance was only boosted by the gain stage of this normal say. Now that itself is getting multiplied by the boost stage, gain of this stage. Is it okay to you? Not clear? I am only substituting where it was 1 plus AGB, okay, and rewriting the same. So now how much is RO effective? It's precisely saying AV1 times AGB times RO1. This into this into this, these are small terms. Okay. So what is the earlier one equivalent we said? AV2 times RO1. Now I multiplied by AGB. Now this AG amplifier could be what kind of amplifier it could be? It could be even another cascode, okay. That cascode may be driven by another cascode and maybe the minimum value 0 finally can be there at the input. So 1 stage, 2 stage, n stages of cascode can bring a desired gain, what boost you are really. Is that point clear? The amplifier I am using can itself be a cascode amplifier which may be driven by another cascode and another cascode and go on till 3 stage, 4 stage, okay, so that the net gain is what you are really looking for, okay. In that case you will be able to get whatever AGB you are looking for, that can be attained without losing what? Bandwidth anywhere, okay. So you just boost it there, no poles will hit you there, so keep doing and then you will get heavily boosted gain in this case. Is that correct? Okay, so what is the advantage of gain boosting?
Might be the chances of oscillation or instability.
Possibility. That is why I say I have not discussed about the stability issue. Yeah, we will come. If there are, this is equivalent circuit assuming very clean stage, but in real life, not only the instability, the 0 will be issue, okay, not the pole as much, okay. The worry may actually come from a 0, okay. The 0 may not be even on the imaginary axis, it may actually lie on the left half plane, okay, which means it will oscillate, okay. What is that it makes? This is a good current source I put there, okay. But this current source cannot be created out of nothing. So it could have a p channel device, it could have an n channel device, it could have a series of 2 devices even there, whose output resistance will also be there. Is that clear to you? The issue is now what? I assume this is a ideal current source, okay. So उसका RO तो infinite लेके जा रहा हूँ मैं, but in real life this may not be infinite. Where that resistance will hit you then? At the output node, whatever is RO here, this RO will shunt it, and if that RO is smaller, all that this cascode work people were doing is useless, because if that resistance is smaller, output is only seeing that resistance. Is that clear? So that is why I say as an amplifier you may worry, you should not use that, because the actual RO may not be very high for normal amplifier, okay. It will be say RD there, okay. Then what do you do? Okay. So RD is the output resistance, nothing RO effective. RO effective is 1 billion ohms parallel to 1K. Okay, so issue was that okay, you have this, you may have more than one transistor in series. Now my worry starts something like this. Let us say for some reasons this is one example, this may be many other, this may be P channel, may be grounded for the heck of it, or maybe I put VB here which is biased something. Now this Vin here, this is my output, this is equivalent to some RO2, okay, or RO3 you may call. Now the one is of course, as I say, what is the major worry? You have boosted RO here, and if this RO3 is smaller, so the output is RO3. So what should I do here? Then I should also cascode the upper ones, say VG2, VGG3 and VGG4. If I do this, yeah, I have the RO of this stage maybe as much as RO of the lower stage, and maybe half it may still be, but at least it is in giga or higher values you can create out of this. But this is the issue, if you are boosting your RO and if you are 3 or 4 transistor in series, that Madam Surbhi was asking me, how do you guarantee this? What is the guarantee of a saturation? A transistor is in saturation if it is VGS minus VT is equal to VDS or smaller than VDS, only then device is in saturation. If that is so, VD1, let us call this VD sat 1, VD sat 2, VD sat 3 and VD sat 4 for this case. For RO boosting you did 4, RO has got what you wanted, goods current source, everything you say achieved. Now you have a issue that there are 4 VDS in series, is that correct? The minimum you have VGS minus VT, VD sat is VGS minus VT one value, okay. Typically how much is the excess voltage? I said 100 200 millivolts, okay. But now you have 800 millivolts, your supply is 1.2 volt or 1 volt at times, keep it saturated, your headroom is practically nil there, okay. So now you are worried that whether this amplifier will remain amplifier for a long, any change in values of VNs or VGS, then I have a problem, this amplifier may not remain in saturation, all transistors may not remain in saturation. If they do not remain in saturation, all the theory which I derived, as she said, how do you know? Yeah, I also do not know, but possibly it is there, that will be lost. So now I am worried that is this a good solution? Okay. If I have to boost so much, I must ensure that I am not using this essentially as an amplifier, is that correct? But this is called telescopic, okay. So I will have shown an op amp which is telescopic op amp, which has its own advantages at some cost. So we like to see that all the time putting things in series may not be that advantageous as it looks. If you have a 3 volt supply, fantastic, no problems. 1.2 there is an issue, and why I keep saying now that is there is issue, because now power supply for digital part is 1 volt, okay, and I am forced to work with them independently. मैं तो bipolar ही करूँगा ना. Why I do all this? Okay, I am doing all this because I am forced to work on CMOS and also on the technology node which is digital node. Okay, so I figured it out. It was not so trivial as I thought. I just thought everything is good, everything is good. Is not really that good as I thought. Okay, so don't use Cascode as a very, though as a concept it is fantastic. No one can beat its concept. Okay, but remember where to use that is a very crucial factors. Okay, we will use in a Cascode op amps, show you. So to avoid this to some extent, I will quickly last few slides I will show you which is the word I used. Okay, I will do this Cascode amplifier with resistive load later. There are two ways of doing this cascoding. One is called normal cascode, the other is called folded cascode. The right is folded, left is normal. What is the difference I did? Here both transistors were N channels. The common gate amplifier transistor was also N channel and the driver was also N channel. Is that okay? However, in the folded cascode, the driver or the input of an amplifier is N channel device, okay, but there is another device which is P type and it's, look at it, it's, instead of going up it's folded down by me. Okay, now you say what is so big about? We will see what is it big about by some things. Okay. Is that point clear? This is called folded cascode. It has advantage of layouts and it has advantage of supply voltage requirements. Okay, both. ये सब चीज़ें रज़ावी के बुक में हैं. Okay, बॉयस बेकर के बुक में भी हैं. Okay, so there is nothing very new I am teaching. I am trying to bring those issues which at times they don't want to hammer on, so I am hammering that those issues. Nothing great is really being told. Okay, I will give the sheets. I will quickly read for you and explain you. Please keep your figure right with you because I cannot put both together, so I will use figure from my lower down sheet and I will show you what. For the first normal cascode, what is, how do we define VOV? Vg1 minus, a source is grounded, so Vg1 minus Vt is VOV. So Vg1 is VOV plus. What is VOV? Vgs minus Vt. Is that clear? So I am just trying to be little funny on that. What is Vd1, which is our VO1 shown there? What is Vd1? Is the over voltage which is Vd saturation plus additional voltage which will allow transistor still remain in. So that is the limit which I want to go to. So we say Vd1 is the over voltage which is Vd sat plus some headroom voltage. Is that clear? What is, why this Vh has been added? With this additional, this also device should remain in saturation. Vg2, look for the term for the Vg2 which is Vd1 plus VOV for the second transistor which is Vgs minus Vt for that, okay, plus Vt because this is essentially Vds of the second transistor, Vds of the second transistor. So it is VOV plus Vtn. Then the Vg2 can be written as substituting here Vd1 from here into this, I get 2 VOV plus Vh plus Vtn. Then I evaluate Vd2 which I get 2 VOV plus Vh plus V2, V0. This small V0 is a average value of a signal which may actually, because of the capacitors there, average value, okay, which can be treated 0 in many cases, but just say swing aya because VO is swinging on the output. So what is the maximum value should be taken care in case it takes you out, then So we want to keep it, otherwise in many cases VO can be treated as a 0 value, but for the sake of evaluation the peak value I should know, I will add that also in my calculations. Is that correct? This small VO is the peak value of the output, which may not be very small at times in a small larger signal. So I assume VO is present, which in normal case is very small and neglected, but for the sake of clarity I say okay, add that also. So I get supply voltage should be 2 VOB, yes, VD2 is the voltage at this node, is that correct? This essentially is this plus this plus this or directly this. Please remember in a transistor whichever way go in a circuit, एक थोड़ी थ्योरी आपको हमेशा के लिए बता देते हैं जो हम सब जगह बहुत इजीली इस्तेमाल करते हैं. If that is not happening then there is an issue. This voltage whatever is V1, if this voltage is V2 and this voltage is V3, V1 must be sign wise V2 plus, this is the game. Either you go through gate and from gate to the drain or source, or you come from directly this. If I want to evaluate this and I do not know some things, so I can go through gate and come to the drain side. Is that point clear? This is one way of doing it, this is what I have used. This method is very strong used in bipolars. Is that clear? This is your VBE, this is your VBC and this is your VCB. So we keep saying when the transistor is externally reverse bias but may become forward bias because this may become forward. Okay. That is exactly saturation stage in bipolar. This is exactly how they do. So this technique, please be clear, at a given two nodes whichever path you come, sum total of voltage must be same because between two nodes this is the difference, okay. That cannot be changed. So method is this or this must be same, loops cannot be go through this or go through this, voltage difference is same irrespective, okay. So tricks of the trade is try games, whichever you know you use that value to achieve the other one, okay. So आप करके देखो, मैंने थोड़ा hurriedly किया है, I may be a small mistake here there, but the point I am saying if I do similarly for folded cascode, please note down that VD2 there, VD2 sorry यहाँ बनाया नहीं था मैंने, I am sorry, she is right. Please remember this is VD2, P channel device, please remember this is P channel device, drain is downwards, this is VS2, this is VD1, okay. Is that correct? The source voltage of P channel is same as drain voltage of N channels, okay. I1 and I2 are the current sources which are biasing N and P device, they may be same, in most cases they will be same, okay. But yes, VO is essentially small one, this is VD1. So VS2 is same as VD1. VD2 essentially is reference to either this or this minus this plus this, that is what I am saying. Normal, either find VD2 is equal to this plus VDS of this, but VDS can be derived from VGS side also. Is that clear to you? I repeat, VGS minus VT is VDS saturation. So I can go this way or I can go through gate and still arrive at the same equivalent values. Okay, try it yourself. Up, the point I am saying is this, VD2 is, what is V1? Raj? Drop across current source. V1 is the drop across current source. So VD2, small AC signal average value plus V1 is VD2. Is that okay? I repeat, this voltage plus whatever is AC on that, which may not be small peak of that. So this value is drop across this plus small average extra value of VO is essentially the VD2. What is VG2 gate voltage? I know this value, I know VOV, so I can reach Vg2, is that correct? So Vg2 is nothing but Vg2 minus Vtp. Okay. Please remember Vs2 is same as Vd1, which is V1 plus VOV plus V0. Then the V supply voltage is Vd1 plus V1. What is supply voltage? This value plus the drop across source, or this value plus Vs2 is same as Vd2. So I calculate V supply for folded cascode is 2V1 plus VOV plus V0. I repeat, V0 is a very small term, but in a larger signal the peak value may not be that small, and therefore we kept it for the security. Why did we keep? Because it should not go that it is taking transistor in linear mode. So we put that value. So if I compare these two values, what do you see really? The V supply voltage of a folded cascode is slightly smaller than V supply voltage of full cascode, normal cascode. So what does that, did we achieve something better? What was the problem I first told you? If I put everything in series, I have that problem of huge supply voltage requirement. So partly I can save myself from that great trouble by putting folding. Okay. Now in this case folded cascode has used N channel as driver, P channel as the other side folding, you can do otherwise. Okay. These are essentially therefore called CMOS folded cascodes, is that correct? The complementary word in digital, they say gates are common, in analog we never say they are common. P and N channel if they are, then we say they are CMOS. Please do not think, at no time, barring exceptions, I should not say at no time, most cases we only use independent P channel and N channel and never use they as a common, so a common gate materials, terminals. So in that sense it is not equivalent of a digital CMOS, it is always both P and N channel have been used and therefore it is CMOS amplifier, is that clear? Otherwise please do not compare it with the other side. So the problem of power supply probably can be taken care by folding techniques, okay, and that is what we will use in the folded cascode op amp. We will actually fold it, okay, to save some supply requirement. See you then.